Hi, everyone. Today I'm going to talk about formally verifying Soroban smart contracts using Certora's Sunbeam prover. So, what is formal verification? According to Wikipedia, formal verification is the act of proving or disproving the correctness of a system with respect to a certain formal specification or property using formal methods of mathematics. So, in other words, it is a technique that allows us to reason about the behavior of a system by checking it against some formally specified property of the system that we care about. The technique of formal verification has actually existed for a long time. In fact, Alan Turing himself asked this question of whether it is possible for a program to check the behavior of another program, which is essentially what formal verification is. And formal verification as a field has actually witnessed several ups and downs over the past several decades. Initially, the field was primarily more academic and theoretical in nature, and around the 70s, there were many prominent computer scientists who laid the foundations of all the techniques that are still used in formal verification. And that was followed by what some might call a dark era of formal verification, where many other prominent computer scientists were questioning whether formal verification can ever be practical at all. These skeptics actually claim that formal verification could never be applied to real world software. However, we have seen that this is in fact not true. Over the past several decades, we have seen many developments and advancements that have happened that have demonstrated how formal verification can be applied to real world software, including verified compilers, verified distributed systems, avionics software, medical equipments, and of course, most recently, decentralized finance applications and smart contracts. So one question that might arise is, okay, well, formal verification seems promising, but when do we use it and where does it fit in our development cycle? And so the answer to that is formal verification can, and in fact, it should be applied as early as possible. In fact, the formal verification mindset can actually help ensure a simpler design of a system, and it can actually help avoid unnecessary complexity, and therefore it can also avoid certain kinds of bugs that are common in complex systems. And in fact, the act of writing a formal specification itself is actually very helpful. In fact, it lets you have a much deeper understanding of the system. We often hear people say that, while they were writing the formal specification, they realized that there was a kind of behavior the system had they'd never even thought about. So trying to think about a system from a formal verification standpoint is actually very important, and it is valuable in itself. Formal specifications that are used for formal verification do have other applications. So, for example, it is possible to generate tests from a formal specification. It can also be used for fuzzing. And of course, formal verification can also be used to improve audits. So when a security team is performing a manual audit of a system, they can use formal verification as a tool to have more confidence in the audit that they have performed. I also want to emphasize that there are certain myths about formal verification out there that are worth debunking, because even though formal verification is a very effective technique, it's not a silver bullet, right? So it's not the case that just because you formally verified your code, that there will never be any bug in your code. Formal verification does improve code security dramatically, but at the end of the day, what it does is it checks whether the program behaves according to a specification. So if the specification does not say anything about a certain kind of behavior of the system, then formal verification cannot say anything about whether the system will have that behavior or not. Another thing to remember is that formal verification should not replace auditing or testing or fuzzing or any of these other techniques. In fact, it should be used to improve manual audits by thinking of it as another tool that you can use to have more confidence in the audit that you performed. And as I mentioned in the previous slide, a formal verification should not be done at the very end of the development, right? So a lot of times we see that once the code is frozen, the engineers are willing to use formal verification, but that is actually not the right way to do it. In fact, the earlier in the pipeline we do formal verification, the better off we are. And the more often we do formal verification, the stronger the guarantees are going to be. So for example, anytime there's a change in your code, if you are formally verifying the code, that means that it gives you some guarantee that you're not going to be introducing new bugs during the changes you performed. And finally, it is also often believed that in order to use formal verification tools, one must have a PhD in formal verification. This is not true. Various domain experts, for example, DeFi developers and security teams, are more than equipped to use formal verification tools because, like most things, formal verification can be learned, and the tools they can be used even if you don't have a PhD in formal verification. So now let's talk about Certora's formal verification tool, Sunbeam, which we have developed to specifically target Soroban smart contracts. So Sunbeam is an automated formal verification tool. It takes as input a Soroban program and a specification, both of which are actually written in Rust, as shown in this diagram. And taking these two things as input, Sunbeam either produces a proof that the code matches the specification, or it produces a concrete violation, as in a concrete input on which the code does not, in fact, behave according to the specification. So that's what Sunbeam does. And of course, in some cases, it is possible that Sunbeam will fail to produce either, and it'll just return unknown, or it'll just time out because maybe the verification problem is too hard for Sunbeam. But in most cases, it'll either produce a proof that the property holds, or it'll provide a counterexample demonstrating that it does not hold. So with a tool like Sunbeam, what we envision is that it will be integrated with the CI or the continuous integration of whatever protocol used Sunbeam for verification. And so the idea here is that having formal verification being part of the continuous integration ensures that anytime a change is made to the code, the new code still satisfies the specification. So you are not going to introduce bugs by accident because the formal verification that is running as part of the CI is going to catch it. Okay, so now we will look a little bit more closely into how Sunbeam actually works. I'm not going to be able to go into all the details in this talk, but I hope that this will give you a high-level overview of what Sunbeam does and what are the key ideas behind the technology. So as I mentioned previously, Sunbeam is designed for Soroban smart contracts. And so it takes two things as input, the code and a specification, both of which are written in Rust. Later on, I'm going to show you how the specifications are written in Rust. And the first thing that Sunbeam does is actually it compiles the Rust code to generate WebAssembly. So what this means is that even though the user writes the code and the property in Rust, Sunbeam actually verifies the low-level bytecode, which is ultimately deployed on the Stellar blockchain. So the way it does this is it takes the WebAssembly bytecode and it has a translation pass that decompiles this bytecode to generate a program in Certora's internal intermediate representation. And this internal representation is called TAG. It stands for three address code. And it's a general intermediate representation that is not only used by Sunbeam. In fact, it is actually used by Certora's other verification tools, like the one for Solana and the one for Ethereum. And so we have this IR that we've developed intentionally to be as generic as possible. And the first thing we do is we decompile the bytecode to generate a program in this IR. And so once we have generated this tag code, we apply a set of semantics preserving program transformations and perform various analyses of the tag to simplify it as much as possible. And so even though we do simplify it, it's important to remember that the meaning of the code is still preserved. So it's semantically still equivalent to the initial program. But the reason we do the simplification is that these transformations actually help in optimizing the subsequent steps of the verification process. So ultimately, when we use off-the-shelf solvers, as we are going to see in just a moment, these simplifications actually turns out really help those steps of the verification process. Okay, so now that we have generated the tag and we have applied various program transformations to simplify it as much as possible, the next step is what we call VC generation, or verification condition generation. So I'm going to gloss over the details of exactly how this works, because that in itself is an entire topic, and we can have a different talk just focusing on that aspect. But I want to give you an idea for what is the key concept behind this. So essentially, what is happening here is that Sunbeam converts the specification, which encodes a property of the system we care about, and the code, in this case, the Soroban smart contract. It converts these two into a logical formula. And the idea is that the validity of the logical formula ensures that the code satisfies the specification. So that's really what is happening. So in the beginning of the talk, if you remember, we looked at this Wikipedia definition of formal verification, and it said that the core technique uses mathematical techniques. And so the idea there, the mathematical technique, is actually essentially converting the program and the specification to a logical formula, and then checking whether that logical formula is valid or not. And so the way Sunbeam actually does this is by using off-the-shelf SMT solvers. So SMT stands for satisfiability modular theories. And there are actually many solvers like Z3, CVC5, CVC4, etc., that can be used off the shelf to solve various logical queries. So the way this is actually done is in Sunbeam. So after it produces a logical formula whose validity would ensure that the code satisfies the specification, Sunbeam actually negates the formula. And then it uses these SMT solvers that I just mentioned, like Z3, CVC5, CVC4, to check whether this negated formula is satisfiable. And we can talk about why this works in a separate webinar. But the key idea is that if this negated formula is satisfiable, then that means that the code actually does not satisfy the specification. And the satisfying assignment actually gives us a counterexample, or a concrete counterexample showing a violation. And so let's say, for example, the SMT solver finds a concrete counterexample following the steps that I just described. That would tell Sunbeam that, okay, well, there is a bug in the code, and then we are going to process it in a later step. And so before we go into that later step, I want to emphasize that in Sunbeam, we actually use what is called a portfolio method. So as I mentioned, there are many SMT solvers out there. So which one do we use? So we actually use many of them together. So we are running many SMT solvers in parallel, and we are configuring them with different kinds of theories, different settings, and we essentially, whichever solver comes back first, like whichever solver comes back with the result first, is a winning solver, and we use the result of that solver. So that's called a portfolio method. So going back to the whole workflow, so let's say that we have queried the SMT solver. The SMT solver comes back with a satisfying assignment of that formula that I described, and that means that, okay, there is a bug. So what do we do? The next step in the process is to analyze the output of the SMT solver and produce a report that is user-friendly, and the user can actually understand what exactly the bug is, how that bug was even triggered. So for example, the report actually has a call trace that has a sequence of function calls, and you can follow the order in which they're called, and then you can identify how the bug was exposed. And so this is kind of the high-level overview of how Sunbeam works, and what are the inputs to the system, and what does it produce as an output, and what are the key steps in the process. So now I'm going to take a simple example and try to understand how we can use Sunbeam on it, and how we can write specifications for it. So here we have a very small Soroban smart contract called increment contract. It has a function called increment. What it does is it looks up the value of this variable called counter in storage. It then increments the value of this variable count, where the value of this counter variable is stored. And then it changes the value of counter in storage and ultimately also returns the value of count in this last line. So given a contract like this, the first thing we need is to think about a property that we actually want to verify, and then we need to write it down formally. So here we have a property that says that after calling increment, the value of counter should be greater than or equal to 1. And so one thing that you can see here is that this is actually a specification, and it is just a Rust function, right? So there is, other than this assertion, this macro here, everything else is no different from other Rust functions that you might write when you're doing development in Rust. And this is by design. In fact, we have developed a specification library in Rust so that Rust developers can easily write specs without having to learn another spec language. You can actually find this spec library, which we call CVLR. So if you go to crates.io, you can see CVLR and all the macros that we have defined there for specifying Rust programs. We also actually have a library that is dedicated for Soroban. It has Soroban specific utilities and macros. There's a separate crate for it called CVLR Soroban that you can also find in crates.io. And you can see that we have a whole bunch of utilities there that you might find useful when using Sunbeam. And so, for example, here, this CVLR, which we pronounce as CVLR, CVLR assert, this is a special macro that we have defined in CVLR, and this is actually interpreted specially by Sunbeam. So when Sunbeam sees this, it knows that it is referring to an assertion for formal verification. Another advantage of having the specification language just being a Rust library is that we hope that this will also allow easy migration between tests and specifications in the future. So now that we have seen a specification for a simple smart contract, you might be wondering, what exactly are we getting by writing assertions and proper specifications using CVLR and then running Sunbeam over just testing or fuzzing? And so I want to highlight two key differences. And the first one is that verification does not make any assumptions about the initial state of the contract. So when you write a test, you have to actually set the initial storage to some value. And then you maybe call a function and you check that some field in storage is changed in a specific way. But when you're doing formal verification, you can prove a property about a smart contract without assuming anything about what the initial state of the contract is. So you can actually say that the initial state of the contract is arbitrary. And because this formal verification lifts this constraint, what it means is that the results of formal verification are actually much stronger than what you might get when you're doing fuzzing or testing. Another advantage of formal verification over testing is that when you formally verify a property, you're checking the property for all inputs. And this is simply not possible when you're doing fuzzing or testing, fundamentally because the way those tools work is very different from how formal verification works. As I mentioned before, formal verification relies on mathematical logic, and it uses SMT solvers to prove whether a property is satisfied for all inputs. And testing and formal verification simply don't work that way. And so it is not possible to test a program on all possible inputs in most practical cases. So to understand this better, let's look at this simple transfer function from a token contract. This is inspired by the token contract from the Soroban examples repository. And what it does is something like the following. So it has this amount, and it transfers this amount from the from address to the to address. So it's a pretty straightforward function. So one thing that we might want to check about this function is that the function correctly changes the balances of the two addresses to and from, right? So you can use CVLR to write this property. So here we have written the specification. First, we are using this CVLR assume to say that, let's assume that to and from are two different addresses. Then what we do is we look up the balances of from and to, and we store them in these two variables. We then call transfer, and then we look up the balances of the two addresses again. And then we write a CVLR assert that essentially just checks that the balance of the two addresses to and from are changed accordingly, right? So to's balance should increase by amount, from's balance should decrease by amount. And notably, the thing that is important here is that if the transfer function satisfies this property, if this property is verified for this function, what we will know is that this property will hold for this function no matter what values we give for amount to and from, right? So essentially, if you can prove this property, you have a guarantee that for all values of to, from, and amount, if to is not equal to from, then transfer is in fact going to increase the balances correctly for both addresses to and from by this value amount. Okay, so now we have seen some examples on how to write some very simple specs for Sunbeam using the CVLR specification language. But Sunbeam we have used Sunbeam to verify much bigger programs than what we have seen so far. And so I want to share a little bit about how we've actually scaled Sunbeam to real-world protocols. And so one thing I want to remind you here is, as I mentioned earlier, Sunbeam actually leverages SMT solvers for verification. So essentially what we do is we translate the tag program corresponding to the code and the specification to an SMT formula. But it turns out that if you do it naively, then it doesn't actually scale to real-world programs, and you might often end up with timeouts and very slow verification times, which are not acceptable. So one key component of Sunbeam that helps scale it to large programs is the simplification step that I mentioned earlier, when after decompiling the WebAssembly to Certora's internal IR called tag. So what happens is at this stage, Sunbeam performs various semantics preserving rewrites of the program. In some cases, it actually inserts sound summaries for some functions that are otherwise too complex to handle. And it can also sometimes learn certain invariants about the program that can, in fact, assist the SMT solvers and prevent the SMT solvers from having to discover them later on. And so these are actually very crucial for helping scale Sunbeam to real-world protocols. Another important part of Sunbeam is its modeling of the various Soroban functions. So going back to that small contract that we saw earlier, you can see that here, even in this small function, there are many interactions of this contract with the Soroban environment. For example, here is interacting with the environment to look up the value of the counter in storage. And so this is in fact inevitable in pretty much all practical Soroban smart contracts, and any formal verification tool that hopes to target real protocols must have a way of modeling these environment functions. And so, even though here, this is a very small program, but if you think about all the library code that is actually included in this tiny program when you make these calls, this actually becomes a much bigger program. And so one option could be that we can simply just decide to reason about all the Soroban library code when verifying a smart contract. But this is not going to be tractable because that is going to be a lot of code to reason about. And for any realistic smart contract, this is not practical. So instead, in Sunbeam, what we do is we have opted for a more scalable approach where we have faithfully modeled some of the core Soroban functionalities in TAC, which is our internal IR. And we've actually found that this is a much more practical and yet a sound way to reason about the Soroban protocols, because when we model them, we try to be as faithful to the actual implementations of these functions in Rust as possible. Okay, so far we have seen how Sunbeam works at a very high level. Of course, we have not gone into all the details. But I want to also mention at this point that we have used Sunbeam to verify several Soroban protocols, including Blend V1, Blend V2, Reflector DAO, and Reflector subscription. Earlier this year, around February, we actually even organized the first ever Rust-based formal verification contest, which used Sunbeam on Blend V2. And right now, we are hosting the second Rust verification contest on Aquarius. So if you're interested in getting involved, if you're interested in using Sunbeam or knowing more about how it works, how to use it, please join the contest. If you're organizing it with Cantina, so you can go to the Cantina webpage and you can find the contest and you can subscribe. And so, of course, there's a lot more to share, but I really hope that with this talk, sort of an introductory talk, I gave you a sneak peek into how Sunbeam works, how to use it for verifying Soroban smart contracts. I also hope I was able to help folks understand what formal verification is at a high level, what it's good for, what kinds of guarantees it can offer when compared to testing and fuzzing and so on. And if you're interested to know more about verifying Soroban smart contracts, please stay tuned. We do have other shorter deep dive videos and blog posts that are coming up in the following months. And if you're interested in looking at the code or using it, you can go to our website. Sunbeam is actually open source, so you can check out our code, and you can also get a key so you can use it on our cloud service. And you can also request audits if you're a DeFi developer. So that's it for today. Thank you for listening, and I hope to talk to you soon.